Okay. Welcome to the part two of the bi-partitioner-based legalization in analytical placement. And so this is going to be a continuation of my talk that I gave last week, where I described different approaches to bi-partitioning in analytical placement, which focused only on those that used bi-partitioning in the solver or in the objectives. And this week, in this presentation, I'm going to be talking about those that use bi-partitioning, focusing only on the constraints or as part of the legalization process during global placement. This will make more sense once I look at the first example, which will be simple. But as a quick reminder, our goal here is to do analytical placement. On the far left, we have a placement solution that optimizes some objective function by relaxing certain constraints. There are constraints such as atoms can't be on top of each other, atoms need to be placed in certain sites or certain tile locations, and we're going to relax those constraints to try and get a hypothetical optimal solution. Then what we're going to do is slowly inject our constraints into the problem to draw the points towards a legal solution that hopefully minimizes our objective. So, and then once we have that global solution, which is a global view of the placement, we're going to fully legalize this through basically what is a cluster, which will do a clustering and then a placement. Yep. I just quickly gave a background on what is bi-partitioning at a high level, and as well as the pros and cons. And I covered two papers. The first one was Gordian, which how it did its global placement is it set up a linearly constrained quadratic programming problem where we're solving our connectivity matrix and our constant vector. This is the same objective we've been doing before. But now we want to add this new constraint matrix, which says, assuming that this block must be in this partition or should be towards this position, and this block wants to be more in this partition, what will my new minimized point be? And we talked about how it constructed the matrix in order to do this and how it chose its cut lines, which it did in kind of a creative way. Next, we talked about bond place, which very strictly said that any blocks, it used a very interesting, what did they use exactly? They used a Hitchcock transportation problem to model a multi-section, which they used to decide which partition to put things into. It then locked blocks into those partitions, and any connections that crossed the boundaries, they basically locked those connections to the boundary of the partition. What this effectively did was it says, in this partition, assuming these blocks you must be in this partition, solve independently. And that ends up, and over several iterations, what you get is a very low overlap solution. So that's what we talked about last week. And also they have very pretty graphs, which I liked. So what are we going to talk about this week? So those past two really had to modify the objective function. Gordian made a linearly constrained quadratic problem, and solving a linearly constrained quadratic problem is harder than just solving a direct quadratic problem. I can just do conjugate gradient and solve that, but now I have to deal with the linear constraints. That makes things a little bit more tricky. I have to do inverses and other things like that. Bond place kind of solved that complexity problem by breaking the problem into pieces. But then you might, by making early decisions of saying you must go to the left, you must go to the right, they had to do repartitioning often, or I assume often, to try and overcome making those early partition decisions early. Another idea, which is was spearheaded by SimPL, is let's use a very simple conjugate gradient solver. It's solving bound to bound, it optimizes wire length, and it's going to find a solution. And then in a separate legalizer, we basically say, what would happen if I took this solved placement, and then fully legalized it? If I fully legalized it, what would happen? And then knowing that information, I can pass that back into the solver and say, hey, knowing that this is what's going to happen in the last iteration, give me a new solved solution that's more informed of that. And by doing this back and forth, solved and legalized, and slowly approaching the two solutions, we can get a solution that is both solved very efficiently and hopefully reduces the overlap. So we're going to talk about SimPL today. And many of you have taken Jason Anderson's Jason Anderson's CAD course, so this will probably be a refresher to many people. So this is the simple flow. We have a uniformly distributed placement, just put the blocks wherever. We then create our bound-to-bound net model, which is we talked about a little bit in, I think, in a previous talk, we talked about this. And then they solve this using conjugate gradient. And a feature, I would say, a feature, I would say, of the bound-to-bound net model is that we had to make a guess as to what the bounds of the nets were. And that is what created our bound-to-bound net model, or that's what set up our matrices. Once I solved this, once I minimized that point, most likely my bounds would have changed. So I have to update the bounds and resolve again and again. And when do you stop? You stop when you realize that the HPWL of the prior solution, the prior bound-to-bound model solve, is around the same as what you have now. Once that happens, we go into a look-ahead legalization, which is going to be the topic of discussion for today. We're then going to attach anchors from the legalized positions, from the movable blocks to the legalized positions in the solvers. And then we're going to do the bound-to-bound solve again. Again, it's just this little loop back and forth until we've converged. And then we go back to doing look-ahead legalization, and we do this again and again and again until hopefully the gap between our solved solution and our legalized solution approaches each other. And what's great about this approach is because we're using anchor points, if you increase the weight stronger and stronger up to infinity, they practically have to become, the legalized solution and the solved solution have to become the same, unless you are hitting numerical stability issues. So finally, after you're done, we do a post-global placement, final legalization, practically a full legalization, doing any touch-ups that may be slightly illegal. And we do a detailed placement where you just kind of fix up some of the placements of the blocks while keeping things legal. That's an overview of the of SimPL. The most important thing that I want to focus on for this presentation is how they perform their look-ahead legalization. What they do is they form a partition line, which partitions the space in half. And this one kind of shows the key insight from this work. We're going to do a horizontal partition here. And notice that it didn't just put the blocks on the top side and the bottom side. What it also did was something it calls linear scaling. What it says is, okay, I know I've picked this window so that its density is just right. So if that was the case, when I create this partition line, I should spread the blocks out so they use the density efficiently. It's their way of trying to preemptively do legalization to save time, and I think for ASICs, it provided them a lot of benefit. And finally, this is just the little graphic that all SimPL-based papers have to have. It is, you have your upper bound, they call it the upper bound or the legalized solution, which has a high HPWL, and we have our lower bound solved solution, where its HPWL should be very low. If not, your solver is not very good. So, and the idea here is that when I have my globally minimized solution and perform legalization, it will just be pretty bad. Things are just legal, put on the wrong side of the chip. Things are really spread out, but they're legal now. We feed that information back as anchor points, and over iterations, the solved solution will get worse because it's moving from the best possible solved solution towards a legal one. But the legalized solution is doing the opposite. It's moving from a solved solution, a legalized solution, towards a more minimum objective solution. And we terminate once this gap becomes small enough. Just a big entry point into SimPL. So separating the objectives from the constraints is a concept I haven't covered yet in this talk. So during the AP flow, two placements are maintained. We have the solved lower bound placement, which is the solution produced by a bound-to-bound solver, and we have a legalized upper bound placement. The naming here is that lower bound, meaning that we're not going to get anything worse or better than this HPWL. And the legalized upper bound is meaning we're not going to get anything greater than, and these bounds will get tighter and tighter as I solve my global objective. And this is a solution produced by the look-ahead legalizer or bi-partitioner. Again, we're trying to look ahead at what the full legalizer is going to do. Now, we're not going to be perfect. We don't want to do a full true legalization here because that's going to be quite expensive, but we're doing the best that we can to get close. And so, yeah, that's exactly what it said. And so finally, anchors are used to draw the solved solution towards the legalized solution. And this is basically informing the solver, hey, solve this again, but this time know that the legalizer did this with your last solution. Now that you know that, try to adjust your solution. So it understands that, oh, this cell is going to be moved across the chip if I try to do the solved position. Maybe I should try moving things in a different way so to allow it more room. That's the intuition behind this.
So they make the pseudonet weights inversely proportional to the length of it?
Oh yeah.
So in other words, the further a cell is from where you want it to be in the legalized solution, the less you weight that. Like I said, the spring will pull on it harder, but it's further away. So they divide by the length. You would get in the energy, you would get a quadratic term length, like the distance.
Yes.
If they divide that to try to, well, they linearize it, they want to make it less strong.
That's interesting. I actually never noticed that because in our global placer, we actually tried dividing by length and it was less stable. But that might just be because bound to bound gets a little funny. So they're actually, when they divide by length here, I think it's a linearization term because they're using a bound to bound solver. However, when we tried this, I actually found that just setting it equal to or proportional to alpha times some magic terms makes it.
That's actually, well, but then you switch to a bound to bound solver.
Oh no, this is during the bound to bound. It was actually very unstable with bound to bound. When I switched to when I removed the division by length, it got a lot better. It's weird.
When you're using bound.
When using bound to bound. Now, granted, maybe we need more experimentation. Maybe our solver is a little finagling.
Interesting. When they're using a bound to bound, they do divide by length.
Yeah. I remember that's the reason why we did this. And finally, one thing I should mention, this alpha term, they grow linearly. Now, we've found that growing it exponentially is a little bit, it converges better, but I haven't tried a linear term in a while. So maybe someone in some convex optimization project could try that and see what happens. Looking at you two. So how do they do look ahead legalization? Big wall of text. I'm not going to make you read it. Step one, so that the first thing we're going to do is we're going to try and find the overfilled bins. What you're going to find, though, is that many overfilled bins are going to be next to each other because things tend to clump together. They're not all going to be on top of the exact same point, but they're not going to be spread across the whole chip. You're going to find that a region of maybe 4 tiles, 4 bins, are overfilled. I don't want to create 4 independent windows, which are then going to get merged immediately. So what I'm going to do is notice that, oh, these overfilled bins are next to each other or relatively close to each other. Let's create a clustering of these. And then we're going to create our windows based on these clustering. You're going to find that basically all of these placers follow this same, all of these legalizers that I'm going to show today, all 3 papers, use this approach. And I also use this approach. You find that it really cuts down on your runtime and also gets you a much better solution. So it's a good idea. So step 1. Find the minimum region that can contain all the contents of the bins within. What that means is I'm going to make a window or in this case, in this paper, they call it a region. I'm going to create a region around my cluster, a bounding box. That's basically all it is. And I'm just going to grow that region until the exact point where all of the stuff inside have just enough space to maintain them. So, for example, I have enough white space, in this case, because this is an ASIC placer, to sufficiently contain all the cells that are within it. Once I've found that minimum region that can contain all of them, we then partition the cells in half. Basically, I have a list of all the cells in that region, and I'm just going to say, everyone to the left, you go on this partition. Everyone to the right, you go to that partition. And it's cut in half by their area. This is important. Different cells have different sizes, so I don't want to do just a counting. where I say you five go on the left, you five go on the right. Because what if those five on the left are massive? So we do a partitioning based on their area. Next, we look at the region and we cut the white space in half. I'll show some pictures to help explain this. And then we're going to move the cells into each region using non-linear scaling. I'll also explain what this means. But as I said, we don't want to make everything snap to the boundary line of the partition. We want to spread them out almost like a squeegee, just so they spread out across the window. That's the idea, or the partition. And then finally, repeat step 2 on each partition. And so this is a bi-partitioning approach. So we keep cutting the space in half, cutting the space in half, cutting the space in half, and we terminate once we have a small enough region that we don't have any overfill anymore, basically. So this is a very good picture from the paper that explains this technique. We have an overfilled bin right here, but what we find is that this one's also overfilled, this is overfilled, this is overfilled, and so on. So what we do is we create a clustering or a bin cluster for look-ahead legalization. That's this big dashed region. Once I have this cluster, we create our window, and once we have, or they don't call it a window, the window term comes in GPlace, which I'll explain later. So if I use window in this case, just know that I mean region. This region will then get cut, we'll make 2 cuts. The first cut will cut the cell area, basically they call it the cell area median, and then our white space cut will look like this. And the idea is we're going to try and move the blocks so that these 2 cut lines intersect. That's the goal here. So we move the blocks. And this is a great explanation of nonlinear scaling. We have our original placement or original region here. And we're going to have 2 diverging paths. The first path over to the right will create these uniform cut lines. Now, this right here is after a partition was made. So now we're going to figure out where to put the cells inside of that region. I should make that clear. What we're going to do is create 10 uniform cut lines. That's the goal. Where one last little trick they do is at obstacle borders, they make a cut line specifically there. So what they say in the paper specifically is each of these cut lines have about 1/10 of the white space. That's the goal here. I don't know why they went with 10, not 12, not 16, but they chose 10, and most of the people who do in the future papers that do this also go with 10. But just know it's a bit of a magic number. We have basically these barricades of 1/10 of the white space. That was one path. Independently of that, we're going to order the cells within that region by in this case, their X coordinate, because we're doing vertical cuts. If we're doing horizontal cuts, we sort them by their Y coordinates. And then what we do is we move the blocks into the windows. So into these sub windows, let's call them. So basically, we're going to put these into 10 equally spaced, or not equally spaced, but equally white space limited groups by using linear interpolation. So they linearly interpolate the blocks. What that means, let me explain this in detail. This block 8 is maybe 70% away from the cut line. If I put it into this window right here, the far left, inside of that window, I'm going to put it at 70% of the way far away from where it's from inside the window. That's how they've chosen to do this nonlinear scaling. Even though it is linear within each of those vertical cut lines, between cut lines is not exactly a linear scale. It's a little tricky, but that's at least my interpretation of it. Cool. It's not super important to understand this. It's just we're spreading out the blocks. So in simple, I wanted to give a summary of how they use bi-partitioning in their legalizer. They use bi-partitioning as a look ahead to what the post-legalized placement will look like for a given solved placement. They're kept completely separate from the solver, allowing the solver to be simpler and more efficient. The idea is, if I put all of my constraints in this legalizer, so that the solver really only needs to care about minimizing its objective, which allows it to be a little bit more efficient. And then we bring in most of these through anchor points. And by using this legalizer, we can resolve most of the overlap and density constraints in an ASIC placer. Future papers will have to deal with the complex FPGA constraints, which we'll talk about in a moment. The runtime of the legalizer is dominated by sorting the blocks. You can look at the paper and how they compute the runtime, but they claim that the runtime of the legalizer is big O of n log squared n. And you can look at their argument for that, where n is the number of cells that you're trying to legalize. And so yeah, this was a very quick overview of SimPL. My goal wasn't to talk about the overall SimPL paper, just showing you how bi-partitioning is used within their legalizer. Any questions on that? Yeah, the spreading's a little weird. Yeah. The idea here is that we're trying to just spread things out evenly so the density we're trying to spread out the density. That's basically what we're trying to do. We don't want the if I were to just snap these to the nearest position. So for example, let me look back at this example. We have this cell area median cut line, and then we have the white space cut line. All of these blocks that are in this region, if I just move this line over, they're all going to go smack on the cut line because they're trying to get as close to their solved solution as possible, which is literally on this cut line, which is going to create a very dense region right here, and which the paper claims is not a very good idea when you're trying to do legalization like this. How we can fix that is what we really want is that the density stays somewhat uniform across this window or across this region. To do that, now, of course, I don't know why they don't just do linear interpolation. I don't actually know why. They chose to do what they call nonlinear scaling, where they create these 10 buckets. Each of these are 1/10 of the white space available. And then we just move blocks into those buckets. That's the nonlinear part. And then we do linear interpolation within the bucket to actually put them in their final position. So you can decide between blocks based on their solved position. It's kind of crazy. And this is used by SimPL as well as HeAP in the next paper, but this is not used by GPlace, I don't believe, or at least they don't say they use this directly.
What line do you go into based on your sorted order, I assume?
Yep.
So they scan a line across, they go, the 8's going to go in the leftmost thing, but then they don't want to snap it. I guess they do snap it to the left border for 8.
Well, they do happen to in this case, but they say they do linear interpolation within based on the solved position of the entire region.
Okay, yeah. Maybe it's just a very complex way to describe that, because it does seem like you could just describe that as pretty much an affine transformation.
It's not quite an affine because you're putting it inside of these bins, and these bins have area. So your 8's not going to go in the far left one, or sorry, number 3 isn't guaranteed to go into the 1, 2, 3, 4, 5, 6th window. That's not a guarantee. It's going to go in 8 and 7 might be just enough area to go in the leftmost one. 5 and 6 might be able to go in the next one. 4 might be in its own. 3 might be in its own, and so on. So there's the nonlinearity in there. Again, we're trying to spread out the density here. If we just did an affine transform, you're not guaranteed, because if everything happens to be all on top of each other, you're not going to spread them out. You're going to keep them all together, basically.
This is because of these obstacles that they're not moving. So because they have obstacles that are not moving, the capacity is varying across those bins. And
yes,
effectively that nonlinear function of how much you move to get into the bin that's okay. I think I get why they're doing it this way.
Yeah. Again, just if they did a fine transform, and these happen to be all on top of each other, let's say, they're all going to get put in the same spot anyways. The density is too high. This is to rip apart things that are on top of each other. Or at least I think that's the intuition. So that was SimPL. Now we're going to move into HeAP. This is the first FPGA analytic placer that I talk about in these slides. What HeAP is if they build off of SimPL and apply it to heterogeneous FPGAs. Now you may say, oh, why don't we just slap SimPL in there and put in an FPGA and call it a day? Well, the problem is FPGA constraints are not that simple. We don't just have white space and we don't just have cell area. We have different cell types that have to go into very specific tile locations, and you can't place a block in the final legalized solution on a fractional position. You have to put them in a tile. So when you make your cut lines, you can't make a cut line at position 2.5. Your cut lines have to be at 2 or 3, because you want to say there are this many tiles on the left and this many tiles on the right. So how does HeAP solve that? This is just a cool little thing just to kind of explain that HeAP is part of is a post-packed analytic placer. But it's an implementation of SimPL for heterogeneous FPGAs, and it performs global placement at a cluster level. What that means is that we use a packer to pre-pack, or not even pre-pack, to pack, let's say, LUTs together into a CLB, DSP parts into a DSP unit, RAM slices into a RAM, and so on. Once I have these coarse-grained blocks such that a block goes into a tile, and maybe a tile can sufficiently hold more, but let's say we're just taking a block, goes into one and only one tile. How do I do analog placement for this? So what was HeAP's legalization strategy? Again, this is going to look very familiar. We're going to create clusters of overflow bins for each cluster. This is just such a good idea to do. We're going to find the minimum region that can contain all the contents of the bins within. We're going to partition the blocks in half. They call this a source cut. We're going to partition the region in half. They call this a target cut. And then they do this one little extra thing, which I'll explain why they do this in a moment. We're going to move blocks between partitions if needed. So before in SimPL, we partition the blocks, partition the area, and now you're locked. We're going to start moving things. You're not going to be able to move to the other side, or at least the paper didn't say so. Here in HeAP, we're going to have to move blocks into different partitions after I've chosen my cut line. And I'll show you why. But after that, we're going to move the blocks into their regions using nonlinear scaling. They use the exact same technique as SimPL. And then we repeat part 2 for each iteration. So what was the issue? Why did I have to move the blocks afterwards? The problem is that you can't create a cut line on an FPGA region right in the middle. Because what does it mean to have half of a tile? It doesn't really make sense, because could I put half the number of LUTs in half of a tile? It doesn't really make sense. So what they chose to do is create their partition lines always on the FPGA boundaries. But this causes a problem. Let's look at the rightmost one and ignore the good and bad for right now. Let's say I was just supposed to cut this in half. I see 5 blocks on this side, 4 blocks on this side. I would say I would make my partition line right here, knowing nothing more about the problem. So because this one cuts it pretty evenly in half. But there's a problem, because when I'm trying to cut my FPGA region, I can either cut this as 3 and 6 or 3 and 6. The issue is that I can never create a cut line, assuming I have this red cut line here for the block locations. I can never cut the FPGA region such that I can actually sufficiently hold these blocks. So what you have to do is actually update the block locations after you've made a choice. So let's say we chose this bottom one, where we have 6 on the top, 3 on the bottom, and I'm going to move this block, this gray block, from the bottom partition to the top partition. That creates this black partition line. Now I have 3 blocks on the bottom, 6 blocks on the top, and now I can sufficiently partition these blocks. So that's why they have to do these extra moves. Back in SimPL, we didn't have to worry about, once we've selected our cut lines, because of how we're dealing with white space and area, it's pretty, at least the paper didn't have to make any special cases for where you had to like move things across the cut line. Now with HeAP, we have to be a bit more careful with what we put on the cut line. That make sense? Or close to the cut line? Cool. So the next thing that HeAP does is how they handle heterogeneity. So recall, with cells, we have area, and some cells are bigger and smaller, but any cell can be placed in any white space. That's not really a big deal. Now that we have FPGAs, you can't put a LUT, or you can't put a CLB in a DSP tile. You can't put a RAM in a CLB tile. So where are we going to put things? So what the paper talks about is that, first of all, the legalization of the different block types are independent. You can legalize the CLBs independent to the RAMs because the CLB tile, you will never find a CLB in a RAM tile, and you'll never find a RAM in a CLB tile. So they can be legalized independent of each other. This is a good idea because it also makes the problem a bit faster. Breaking the problem into independent pieces allows us to solve it more efficiently. This is not a bad idea. And the problem, though, the consequence of this is that according to HeAP, different types of blocks may be moved to opposite sides of the device, and they claim that that can cause an issue. For example, imagine if I had a CLB and RAM that are really tightly coupled. Or let's make it even more interesting. A DSP and a RAM that are tightly coupled. Let's say they have strong connections with each other. And I put them right in the center of the chip. Let's say the DSPs are on the left and the RAMs are on the right. When I do my legalization, they're going to get ripped apart because the legalizer has no understanding that these two want to be connected together. What happens now is that now the solver has to do more work to figure out, okay, these are moving farther and farther apart. I need to start reassembling my global placement in a better way. How they handle this, I actually am not the biggest fan of, but they claim it worked well, so I'll talk about it. What they propose is that we're going to fix different block types during the global placement at different times. The idea is quite simple. I'm going to let the CLBs move, but I'm going to lock down the DSPs and RAMs in their current legalized position. DSPs, let's say we only have CLBs, DSPs, and RAMs. I'm going to lock the DSPs and RAMs, solve the CLBs. Then I'm going to lock down the CLBs and unlock the DSPs and solve them. Then I'm going to lock down the DSPs and solve the RAMs and then lock them down and so on in a round robin fashion. And they actually do it in 3 different ways and compare them. So first of all, nothing gets locked down, movable, everyone's happy, no locking down any blocks. Rotate is what I just described. I lock down one block, I unlock one block type, leaving the others locked, and then I round robin around. Finally, I talk about this last case where you unlock all of them, then you unlock just one, then unlock just the other, then just unlock the other, and then you unlock all of them in a round robin fashion, almost like all is another block type, for example. And these are the results they brought up. Now, what they found is the most stable results, which gave the best HPWL, is the all plus rotate. They argue that the all phase of this gives them a bit more of a global view of the placement. And the rotate allows things to be more stable when they're moving during legalization versus the global placement. I'm not super convinced of these results based on what I'm finding, but this is a cluster level placement, and I'm using a flat level placement. So, and I've never actually tried this experiment directly. So it'd be interesting to try this out in VTR, but I find this a little hard to believe because I do find that we converge quite well even when we're just doing the all approach, but I'm not sure. Something to try out. Any questions on how they handle heterogeneity here? It's a pretty cool approach.
The anchor points are removed every iteration, right?
So you
basically get anchor points, solve, spread, get rid of the old anchor points, put in new anchor points.
Correct.
Yeah. So the problem of like that they're highlighting, these two things can be moved in opposite directions. It's true, but ideally the solver would
exactly
fight it the next iteration.
That's where I agree with you, Vaughn. I would think the solver should be the one dealing with this because the solver has an idea of the objectives, but they say it's more stable. That's the word they used. And notice that I'm finding you do see the HPWL is on the same order, but you do get a bit more of a stable convergence. So that's a good argument for this. And that is something I can agree with, but I'm not sure if it's necessarily good. They say it's going to give you a better HPWL, and that's not something I agree with. Because I think always having a global view might be a better approach.
Why do you think setting fixing the blocks in all plus rotating actually helps with that?
The idea is that because eventually these are going to get locked down. What you're saying is, imagine I lock these down right now. And let's say we had a ton of CLBs. If we're assuming the DSPs and RAMs are in a particular place, the CLBs will make a different decision than if everything's moving at the same time. It's how do I describe this? It's
let me just give like an example. So I'm saying if DSP blocks just in a couple calls.
Yes.
Which some chips have. So you can have the solver basically kind of go, I'd like to put the DSP blocks over here, and this logic block should go right around it, and it's not really near that column. You know what I mean? Now the anchor point should move it back eventually, but you can see how it could be more problematic in convergence because it keeps moving stuff away from this column and converging around. I like putting the DSP blocks over to the left some more. I'm gonna put the CLPs right around them. You go, you can't do that. And over time, I guess like your anchor points will get stronger and stronger, so they eventually should fight it all the way.
Yeah.
But I guess I can see how you can get convergence issues. You just lock it down. You got to stay where I put you. Everybody else optimize around that. It'll be mostly the logic blocks probably that optimize around it. So it's kind of like okay, put you in column, stay in column. What would be a good logic block arrangement? You ready?
Yeah.
So,
And discussing on that, this optimization really is for CLBs. They do even claim in the paper that the number of DSPs and RAMs are quite small. So their iterations, when you lock down the CLBs and you're just doing DSPs, it's much, much faster. The number of blocks is very low. The number of things you're legalizing is very low. So it's not like you're really losing much from doing this. You're just spending some extra time assuming that let's let the DSPs move while the CLBs cannot.
this is also where benchmarks matter, because I don't think their benchmarks are nearly as big as the ones you're using.
Correct. I'm not sure. I actually not know what benchmarks they were using. They were using something from Quartus.
They might be using quick benchmarks, I'm not sure, but they're probably not as big as what you're using.
Yeah, you're probably correct, actually. But I haven't tried this exact experiment. This is just my intuition from working with this for so long.
And they may not be as heterogeneous. I mean, I can't remember for sure, but basically there's often a thing that happens in, well, many papers, like your benchmarks are lagging, right?
Yeah.
You got benchmarks that you got handed down from the ages, right? Because people guard their designs pretty zealous, like, so maybe your benchmarks are kind of old, they don't actually have, they're not very heterogeneous, so.
Yeah, if we had more time, I'd show, but I'm just going to continue to move onwards. So, an overview of how HeAP does bi-partitioning. It's the same look-ahead legalization strategy as simple. It practically is the same if you just draw the map out, but with improvements to handle the more complicated constraints of heterogeneous FPGAs. The partition lines must be at tile boundaries, and the consequence of this is that we now need to allow blocks to move between partition lines after a partition is chosen. And the heterogeneous block/tile sites lead to independent legalization problem. The problem is not a negative here. We can do independent legalization problems. It's not a negative. And how they solve this is locking down different block types during global placement. Any questions on HeAP? It's a very cool approach, and it was very early. Like SimPL came out in 2011 with an updated paper that I'm using for reference here in 2012, and HeAP came out in 2012. So they applied this pretty much instantly. So it's an impressive work. GPlace 3.0 is a much more modern placer, analytical placer. It was one of the ISCPA or ISPD analytical placers, which they had this massive competition where like a bunch of different schools tried to compete to create the best analytical placer for a Xilinx architecture. And this was one of the entries. So this one is from 2018. It's an FPGA analytical placer, and it also separates the bi-partitioning into its own legalizer. So it's one step up from HeAP and simple. It's no longer simple. So
You know how you like names for papers?
yeah.
So your paper should be, the next paper could be complex, where you capitalize the PL.
Oh, that's great. Well, that's great, actually.
I'm not sure that actually advertising this is complex is a good idea, but I was thinking like, you love dates.
Anyone want to know why it's called GPlace?
Name of the author?
Is it global placement? Because you're wrong. It's actually Guelph.
Huh.
So this is from the University of Guelph, so it's GPlace. But I think GPlace would be funny. Anyways, so as you can see, a big difference between HeAP is that this is now working on a flat net list. We're at the primitive level now. We pass this in, and I'm going to ignore the pre-placement. What we're going to do is a wire length driven global placement stage. And notice this is very similar to SimPL. We have a solver, which is going to give us a solved placement. And then we have a window-based legalization, which is going to give us a legalized placement. And then we're going to try and converge them towards each other. Now, they're not using bound-to-bound like what HeAP and SimPL used. We're now using something called a star plus model. I'll talk about that in a moment. They claim it's a more accurate representation to how post-routed wire length will be for a FPGA. Whereas HPWL will usually underestimate how much wiring you're going to use. They claim this will compensate for the underestimation. And the window-based legalizer, it's a lot like HeAP. We're going to separate the legalization of LUTs from the legalization of flip-flops, from the legalization of DSPs, from the legalization of BRAMs. And they're also going to do some tricks. They know more about their architecture. They say our architecture is a Xilinx architecture. We know exactly how LUTs are going to be shared. We know how flip-flops are going to have certain constraints on their clock signals, on their reset signals, on their enable signals. And I'm going to talk about this. We're going to put those constraints into our window-based legalizer. And they claim that this window-based legalizer gets them so close that they don't need to pack. Now, I don't know what that means. They say they don't do packing. Now, does that mean that it's a fully legal solution? I don't know. They just say that it's so good, doesn't need to pack it. And notice that this is split into two phases. Phase one, no extra information, just standard global placement. Stage two, what they're going to do is they actually run a full router, basically a VTR style router to try for a few iterations to try and figure out where the congestion is in the circuit. Once they know where the congested regions are, they inflate the LUTs, so they take up more space, that's what they call it, so that now the LUTs are much bigger, and so they'll take up more space, so hopefully we'll spread out the congested regions. And then we do the same global placement again, but again with these inflated cells. And then finally we do detailed placement, which is a bit complicated, and I'm not going to talk about in this talk. So, as a brief summary, it's similar to SimPL. They maintain a solved and legalized placement. They use what's called they call it a Jacobi solver. It is conjugate gradient, or it's conjugate gradient based. It's a little complicated if you read the paper. It's weird. Which optimizes the star plus wire length model. Again, star plus is supposed to be a more accurate estimate for used wiring in an FPGA than HPWL. And it's not formulated as a quadratic equation. Now, I still consider this a quadratic placer. And the reason why I do is because I'm a kind of if it quacks like a duck, it's a duck kind of person. They're separating their solver from their legalizer, which is very similar to how quadratic placers tend to do this. And when you actually dig into the mathematical formulation of their star plus model, they're using conjugate gradient kind of as if it was a quadratic model.
Jacobi solver, it's conjugate gradient, but Jacobi is a simpler iterative technique for solving a matrix.
They do both. It's weird. I can.
The Jacobi is such a simple technique that in second year I coded it up for a lab.
Yeah.
It was a mandatory lab.
So,
it's fine. Like, it's not like bad. All it is you just go through row by row and you basically update a variable by figuring out what the error is. Take that row, multiply it by the vector on the other side. It's not going to be equal to the b. You figure out what the error is, and you go after update this one variable. And you go to the next row and do the same thing. And SOR is a slight enhancement on that.
Yep, so they're basically trying to do SOR. So when they say Jacobi, I believe they mean SOR. I don't know the relationship between the conjugate gradient method because they show both in this paper. This is the StarPlace paper. StarPlace came out before GPlace, before GPlace 2.0, before GPlace 3.0. Welcome to GPlace 3.0. And the math is fun. I actually really recommend you read this paper if you just took a convex optimization course. I'm gonna keep poking at you guys, but they do talk about a lot about this.
So
but
they play with whether they use conjugate gradient or successful relaxation.
I think they do play with it, but I don't remember.
Like once you get like a matrix, you've got a bunch of ways to solve it. And technique is three different very closely related techniques. So Jacobi, Gauss-Seidel, and successive over relaxation, but they all basically work that same way.
Yeah.
Just update one variable and figure out what the error is if I multiply this row times the current solution versus the b value that's supposed to be.
Yeah, but the basic idea though is that it really is really close to a quadratic global placer to the point that I actually I classify this as a quadratic placer, even though it technically isn't quadratic. And they also use a window-based legalizer. It bipartitions the space to remove overlap similar to SimPL, but it includes other, I shouldn't call it objectives. I want to be careful with my naming here. They include other constraints to handle the other FPGA constraints. And that's going to include things like LUT sharing, clock regions, reset signal sharing, etc. And they claim that packing is not necessary with this approach. Once you do full legalization, it's packed, which is a bold claim.
I'm sure what to say is true. They're targeting a simplified variant of the ultra-scale architecture.
Correct.
On relatively simple benchmarks that don't have carry chains and so on, unless they've changed it for this paper, but the ISPD benchmarks have no carry chains. So you wind up with The only packing constraints you have are these clocking constraints kind of thing, and you don't use, and essentially the 5 light versus 6 light sharing. So you have some, but you don't have like an enormous number of like packing constraints.
Right, and I think I agree with you. I didn't see carry chains in this paper, but I should be clear, GPlace 3.0 is not the submission to the ISPD. GPlace 1.0 was, I believe.
Yeah.
This was
I know
the
ISPD ones don't have any carry chains, but if they've added some industrial circuits, then we have them.
Yeah, I'm not sure entirely. But you're going to notice that it's a very similar thing. Again, we're going to be clustering these. It's a good idea to cluster these. I'm going to keep nailing it home. I didn't originally cluster it. Biggest mistake I made. I add clustering, it made it like 10 times faster. It's so much better to do this. They have these legalization windows. This is the first time I've seen windows being used in this case, and I like the term windows over regions, so I'm going to use windows. We're going to create these windows, we're going to merge the windows, and then we're going to spread them amongst the windows. I didn't find anything to do with nonlinear scaling here. So they are just doing bipartitioning over and over and over again. Now, merging the L windows, they give a large focus on merging the windows in their paper. From personal experience, when I worked on my bipartitioner, I have found that doing flat placement, creating truly minimum spanning windows is very important. If you overestimate by making your windows too large, things spread more than you expect and things take way longer. Because if I made the window too large, I'm going to start picking up blocks that are not already pretty legalized and start to move them farther away from where they want to be. It causes a lot of problems. So trying to actually create truly minimum spanning windows is very important. So they spent a very long time in this. Yep, so blah, blah, blah. Bipartitioning relies on reducing density. So increasing the density of the parent window can reduce the density of the child windows. Bad Z. So decreasing the density. Sorry about that. If I make my window too big, the density is going to go down. And it's because I have more area and less blocks within. So, but decreasing the density of the parent window can reduce the density of the child windows, which is not what we want to do. We want to fill them as much as we can. Or as close to our target density as possible. Prior to growing the windows, they perform preemptive merging. Basically what they say is, I have these two clusters. Let's estimate how big those windows are going to be. Oh, the estimation shows they're going to overlap. Let's merge these together into the same cluster. It's just a good idea to do this. And after growing the windows, if two windows do overlap, we rip up the windows created and we combine the clusters and then we regrow the windows. This is so that if you just take the bounding blocks of the two windows, it's going to create too big of a region. So you recombine the clusters and try again. And I think this gives them even more tighter windows, which is not a bad idea. And this is their window generation code. Again, I don't want you reading all of this. It's kind of crazy, actually. The goal, we want to quickly find the minimum window which can contain the overfilled cluster. Aggressively grow the window. What they do is they take the largest dimension, multiply it by 2. Take the largest dimension, multiply by 2. Or, sorry, the smallest dimension. And multiply by 2. They're just aggressively growing the window. Then they binary search the larger dimension to find the smallest size that it can be. And then finally, they fine-tune the window on all sides by decreasing it by 1 until it gets very tight. And
so this is like just basically finding the area in the grid that would give you enough resources to
yes,
handle it? Okay.
Just enough. Not too much, not too little, just enough. And that's the goal here. So I'm sorry to rush through this. We're just running a little low on time. Other legalization objectives. So LUT sharing. 1/6 LUT in their architecture can implement 2 LUTs if they share sufficient numbers of pins. What GPlace 3 does is it pairs LUTs prior to legalization based on their solved positions and locks them together. So if it says these 2 LUTs want to be close to each other and they share sufficiently enough pins, let's take this one and throw it away and say that they're locked. Wherever this one gets placed, that one's going to get placed as well. So they basically do like a pre-packing, a lot like our molecules. But they do this on a per legalized basis. So after the solve, they basically do another pre-pack almost, if that makes sense. Flip-flop control sets. So slices on their architecture have constraints on how many clocks, enables, and reset signals they can have. What GPlace does is it maintains a tree structure organizing the flip-flops in a circuit during partitioning. And I'll show what this tree looks like. And the tree practically packs the LUTs together into groups that can exist in the same cluster. So for example, my slice can only have 2 clock signals. So if I look at all the flip-flops in my region and find 3 clock signals, I know that 2 of those can be in the same cluster and the other one has to be in another one. And they use a tree structure to efficiently do this. I'll show a picture of this. And it's used to identify overflowing regions and picking which partition different flip-flops go into. If you all share a clock signal, you guys are very related, I'm going to put you in the same cluster. That's what they do. So this is what that tree looks like as promised. We have all of our flip-flops as the roots, as the leaves of the tree. And what we have are all these 9 flip-flops all share the same clock enable. These 5 share the same clock enable, but a different one. And these ones both share the same reset signal, and they're all part of the same region. And what the idea here is that by knowing how many slices are going to be in this region, how many slices are going to be in this region, and so on, I can get an estimate for how many slices there's going to be. This is actually how they estimate how overfilled a region is, by looking at how many slices they're going to need to fill it, or how many slices they're going to need to sufficiently implement these flip-flops. And then they also use this as, for example, let's make a break here. These ones are all going to go in one slice, maybe a break here, and so on. That's how they do their partitioning. As you can see, they're doing a lot more than just saying, okay, you guys go on the left, you guys go on the right. They're actually looking at how different flip-flops share their signals to decide which partition to put things into. It's injecting more constraints into their bi-partitioner. Kind of important. So as an overview, the approach is similar to HeAP and SimPL. It's a window-based bi-partitioning, with heterogeneous blocks are partitioned independently, and they solve and legalize at the primitive level. They add more constraints to their legalizer to create a more legalized placement, to the point that they say packing isn't even necessary. I did not verify that claim. They are very careful with how the windows are constructed to ensure they are minimal. And finally, they use a 2-stage approach where congestion information from the first stage is used to improve the second, but the global placement is the same. I just like this approach, so I thought I wanted to just mention that as my last bullet point. Okay, I am 2 minutes over. I am so sorry, but anyways, any questions?
This is an observation. So compared to Mongrel, which David Grant was talking about, yeah, I guess the key difference is Mongrel actually keeps track of what it's doing to wire length as it spreads out.
Yeah, but it understands the gain function.
Yeah, none of these have a gain function except for
the first 3. Well, the first 3, these are the ones I talked about today. You're right. But the first 2 that I talked about, which was Gordian and bond place, they did, because they put partitioning in the objective function, it is doing both.
I think the cut size base, if they run a partition, if they actually run a partitioner, they'd have a cut size based objective, but they didn't directly optimize wire length either, did they?
It's in the objective. So because Gordian, for example, makes the cut line and then solves the objectives with respect to those cut lines. Oh, I guess when they make the choice of the cut lines, yes.
I guess, yeah. I mean, they Gordian makes center of mass constraints and goes back and resolves. These other ones on the right are using anchor points and then they resolve. So they do different things in terms of how they encode information from the partitioner back into the solver.
You're right. These 2 are different. That's why I made that. Yeah.
Yeah. And I think bond place was also, what I think, it was snapping things to the edges of blocks and so on, and then putting that back in the objective function and resolving.
Yeah.
But I guess an interesting thing about Mongo compared to everything I think we've talked about so far is as it's doing the legalization, it actually understands not just am I trying to move you to an empty spot, but as I move you towards an empty spot, is your wire length going to get worse or better?
Yep, I think I agree.
I'll try to move you, I'll try to find a path that moves a bunch of things a little bit, such that the wire length doesn't get worse or gets worse as little as possible.
I agree. However, I do think Mongrel is in a different category. All of these are doing this during global placement. I think Mongrel is a full legalizer that happens at the end.
That's interesting. So they didn't, I mean, that's interesting. Okay, that's a good point. So you're saying that's only their final legalization.
Correct.
Okay.
Because if you try to do
otherwise,
because if you do a flow-based legalization, I think it's or a ripple-based legalization every single global place iteration, that could be very expensive.
Yeah. Okay, good point. Thanks.
Yeah. Any other questions? All right. Any questions online before we hang up? All right. Thank you guys so much. Let me just end the recording.
Thank you, Alex.